So this is probably one of the hardest working hacker teams that we had at the hackathon. I know this for a few reasons. One, I poked my head in a couple times in the middle of the night one, to make sure that my arch nemesis hadn't topped my high score at Donkey Kong that we had set up. And two, just to see how everyone was doing. And I think this team was probably here almost a full 23 hours. And I'm going to turn it over to them if they're all set. You ready, guys? Okay, remember, you have 20 minutes, including Q&A. So take it away, Team Oogway.
Okay, so like you said, our team name is Oogway. My name's Matt Wallace. I've got about 6 years of development background and been working in the Pi system in a few different roles for about the past year.
Yeah, I'm Kshitij, and I've been working with Pi system for 8 years now. I'm a Pi developer.
Yeah. Hi, I'm Pauro Joshi. I have been working with Pi system 5.5 years. I'm currently working as a technical lead in ECG IT.
My name is Diego. I'm a data scientist, kind of starting to work with Pi, but some good experience with statistical modeling and statistical programming.
So we kind of had a quote, if you will, and an overarching theme that we were thinking about as we were going through the hackathon of there are no accidents. And we took this back to the concept of our team, right? So we didn't just end up on a team by random. We got data about each other. We knew our backgrounds, and that allowed us to make a more informed decision, right? Isn't that what we're all trying to do, right? We've got data on our facilities, on pieces of equipment, on people, on how you want to move them around the facilities to be more efficient. So this was what we had in mind as we were thinking through the problems. And so there was a few different things that we looked at. They give us three main problems, but we wanted to go over, okay, why are we here, right? What things are we trying to enable by working in the hackathon? So the first one, we want to enable better decision-making, derive operational excellence, right? We don't want to be making gut decisions. There's some things that you have to go off instinct, but you want to be able to use data and information to drive that. We wanted to enable aggregated visibility, right? So as you have all of these facilities, you don't want to have to go down into each facility in a graph or a table to look at that information for each of those. I need to be able to see that aggregated to be able to make decisions faster. We wanted to create one place to go to answer those questions. We didn't want 5 or 6 different dashboards, so now I need multiple monitors. We wanted to create one place that you could start at, a landing page that then allows you to drill down from there to get to the actionable information that you're looking for. We also wanted to build the foundation, right? You don't want to have one-off solutions that then every time you go and you say, okay, well, I want to add this, but I can't add that to anything that I already have, so I have to stand up new infrastructure. I have to create new applications to extend upon that. So we wanted to build a foundation that we would allow to be able to add to later, right? To extend that out from what we already have. And then when it comes to the data, once we free that a little bit and make it more readily available, that's going to enable some automation. And so how we did that was we went in and we built a dashboard. These are some of the things that have went into the dashboard that we created, and then we'll show you a few examples of that here in a minute. So the first thing that we did to be able to build our application was we started keeping track of which booster or which plant was receiving gas from each booster. To take a step back, the main thing we were trying to figure out was routing efficiency. So we have all these boosters out there and they're sending gas to the different plants. But to be able to do everything that we wanted to be able to do, we needed to know what we're currently sending to, right? So we started tracking that information within AF. The other thing that allows us to do over time is you can start to run analytics after the fact to see were we running more efficiently and create other models off of that information. So we use mapping technology, so Google Maps, to go in and give visibility to which boosters are sending to what plant. To our knowledge, there wasn't an easy way to see that. You could have that information, but I couldn't just look at a map and say, here's all my boosters. Okay, these 2 boosters are sending to this plant. So the other piece that we stepped into was build within that same dashboard that we talked about. We made it easy to see which boosters aren't optimally routing, right? So if I've got my 10 boosters and I don't make as much money by using this one, I need to know which plant I should send that to be making more money from that. And then we wanted to allow the drill down for each booster to get into some of that maintenance and efficiency of a given booster station. So now we can dive in and see what our application looks like.
All right, so this is the landing page Matt was just talking about. So the idea here is to provide a visualization to, to better understand and keep a track of where the gas is actually flowing right now. So we actually, this information was not available in the data that we were given by DCP. So we actually made up this information like plant booster A is sending gas to plant A. So, oops, I'm sorry. All right. So here, this is the Google map, which is showing like what the current state is, which booster is sending gas to which plant. This is a simple visualization, and it has a drill down feature, which we'll show in a couple of minutes. And then after using this information, keeping it as a baseline, we created an algorithm which actually determines how is DCP actually performing right now. So if you are routing your gas optimally or not. So based on that algorithm, we come up with this table up here on the top. If you see, the first column shows the list of the booster stations within a region. And then the next column is the current plant where each booster is sending gas to right now. And based on the algorithm that we created, we come up with the optimal plant, which is column third here. So you can actually look if this booster is sending, if you need to read out the gas to make more profit. And the fourth and the last column is the percentage margin, like in the profit, which I can make more if I read out the gas based on this. I can actually zoom in a little. Yeah, so this might be readable now. Yeah, so the first column is the booster station, second is where it is sending it to currently, and the third one is optimal plant based on the algorithm that we have written, and the last column is the percentage difference, how much more you can make rerouting it based on this table. And below it is just another representation of how each booster is doing right now. So if you read out the gas from these boosters based on the table up top, based on the recommendations from the table, you can make this amount of extra profit from that particular, transporting the gas from that particular booster. Yeah, and about just a little bit more details about the algorithm that we have written. Paura will just talk through that.
Yeah. So the algorithm we made. So the algorithm in the end it is showing how your each booster, how much your profit margin you are losing right now. So algorithm is made in two stages. First stage is each booster has been compared against all plants it can send gas to, and what is the best profit margin I am getting in. So that's the first stage. In second stage, we get the collaborated view. So if one plant is receiving data from two boosters and the capacity of plant is allowing only one booster, then how should I make a decision? So that decision is based on profit margin, and that profit margin is calculated and on the equation like gross margin minus the distance, and 2 cents has been given as per mile cost. So distance into 0.2 that has been subtracted from the gross margin. So we came to profit margin, and that profit margin, based on profit margin, we decide this booster should be given gas to this plant. And so there is another case where plant can be used maximally by giving two boosters to the same plant. So that has also been covered in our algorithm. So now when we click on map, so we can go deep to booster station view. So Diego will explain about booster station view.
All right, so now we know to which plant each booster is sending gas. We also know what is the best route to be used for the gas. And the next objective would be, how is my equipment doing right now? So the approach we decided to use for this problem was, let's focus on the compressors, on the boosters itself, but let's try to do a little bit more data science approach. So the three main focus that I took for this approach was, first of all, I focus on the anomalies. So this is a concept that I use a lot on my projects, because this also helps us to understand how good is your data. So basically what we do here, we look at the distribution of your sensor data, and see if your points are behaving the way they're supposed to behave or if they are working as outliers. So this may help us to ask some questions. Okay, is my data looking okay, or is my equipment not looking okay? So here we have this logic built on the AF trying to find those anomalies. The second aspect we took was the trending attributes. We know that an operator can look at a trend and say, okay, this is going up or this is going down. But what we want actually is the computer doing this job for us. So in other words, we have some logic written again, reading the values of some training attributes, and we took those training attributes based on the recommendations DCP gave us on the business case. So by looking at this example here, and this is real data, this is running on the AF right now. So we have, for example, RB vibration trending downwards, and at the same time, we have LB vibration trending upwards. For coincidence, in one of the studies we made in our company, we had a trend like this that led us to a very bad failure. So this was the second approach we took. So in other words, we are looking for anomalies in your data and looking for training attributes. And what we do with those two guys, I mean, what is the main conclusion we got? And the third approach is by looking at the compressor itself, we started to use the concept of remaining useful life. This is a concept that we are using in one of the projects in our company as well. That means, okay, nowadays, you look at a temperature, for example, you know that the temperature is going high, you know that this may drive you to a failure, but when this failure is going to happen, we don't know. So what we try to do here is, again, to use data science to do some regressions behind the scene and plot this future data and say, okay, if you continue operating like this, you're going to take this amount of hours to reach the target function that you gave us. This target function could be a temperature, could be a pressure, or it could be something more robust, like root cause analysis conclusion, for example. So by having this target function, we do the regressions behind the scene. There are several methods that can be used. And then this number could help us to kind of plan our maintenance better. So this is, again, there's much more that can be explored, but given the time we had, like 24 hours, we decided to go to this 3 routes, so to speak, which is my data looking good? I mean, do I have anomalies? How is my training attributes going? And how many times can I operate like this? So yeah, now let me go back to Matt.
So this is the application that we've developed so far. We could jump in and show a demo of that later if you want, but we figured screenshots would get us there a little bit easier. And so after seeing this, right, so what's next? Like we talked about in the beginning, we wanted to build this foundation that we could expand upon later on. So the thing that we want to look into next, and he touched on it, but one of the things that we think would be powerful is to get better insights into the remaining useful life of the equipment. That was up at the very, very top of that one. We think that would be really helpful to have, but we didn't have time to go in and do that.
Yep.
We want to add metrics to the map to quickly see the issues. So on that map, when we first showed it up, you could see each of the booster stations and you could see each of the plants. We want to be able to hover over that one to give kind of whatever KPIs are most beneficial right there. So whether it's efficiency or some of the anomalies that he was talking about in the data, to be able to roll those ones up. We want to enhance the map to include all regions. So for the things that we were doing, we were using the templates. We just focused on one region to get in there, but since we're using the templates, we should be able to take that and send it across all the fleet and tie that in with the map visualization. The last piece that we wanted to do was build a dashboard to view regional roll-up efficiency. So I want to be able to compare each of my regions at a glance. Right? I don't want to have to go to all these different dashboards in it. I want to start top and then be able to drill down. We just kind of started a little bit lower to where you could see each of the booster stations and the plants that were there. And so the whole overarching theme, like we were saying before, that there are no accidents, this comes to the fact of there's all this machine learning and AI and everything out there, but what's still most powerful is if you can pair that up with a subject matter expert, right? Give them better insights and information to look at to begin with, and then they take what they know, being the subject matter expert, combine the two, that's what's going to give you your best decision going forward. Thank you.
Pitch panel.
Good job, guys. Couple of questions from me. On the, I like the, this is a comment, not a question, but I'll get to the question. I like the map, and I like the kind of the abstraction of the map model. I think sometimes we get too hung up on, I got to know the exact shape and route of the pipeline between the plants, and to do an optimization, you don't really need to know that. You just need to know something about the constraints and kind of what the, so can you talk, I mean, you talked a little bit about it, but I'd like to hear a little more about the optimization, modeling, and ability to, I guess my question is sort of how extensible is that?
Yeah.
If we need to just keep adding constraints or optionality, is it built to be scalable, or is it built kind of custom
Yeah.
for that set of assets?
So the current constraints that has been given is like each booster can send to only each booster can send all of gas it to one plant. So we can, so there is in AF only we have some attributes, so we can directly make it is scalable because it is template level. The second thing is we are getting like which are the boosters and which are the plants each booster can send the data. It is based on the category level that is defined in AF. So it is, if you just add one category, or if you just add one element category in that any element, AF element, it is directly considered in the equation. If your plant is down, it will be also considered because we are taking the current capacity the plant can take. So it will be changed in your pi data, and if pi data is updating in AF and so everything is fine, we can directly calculate. And if your booster goes down, then also because it is real-time algorithm, it is not algorithm that is static on 1-to-1. So on the because we asked the DCP guys, they said daily we have to check that which plant we should send the data to. So it's very, you just run algorithm and it will automatically update your data in AF. So we are getting data out of pi. We are calculating using C# and AF SDK, and we are sending back to pi. There are AF attributes we created like optimal plant, the cost margin factor, margin profit, that is 1 point something, whatever we can get. Current plant we are sending. So current profit margin we calculated because we have now our equation. So we just get plant to that distance and all, and we calculate current profit margin. And there is the third thing is just comparison, because comparison we need two. So we made that current plant thing, we made like a static one because we don't have currently information. But yeah, that's how we calculated. So it is very much extensible.
Great, thank you for that. One more question from me on the, I think the data science thing is super interesting. Talk a little bit about your and you know, I realize you guys only worked on this for like 24 hours, but talk about your confidence level in the useful life, and then when you say on here more insight into useful life, or how close or how far away are you from, hey, what are the factors that are driving the remaining useful life, so then we could potentially go do something about that would extend the useful life.
Yeah, so the confidence level, it all depends of how many trending attributes are we considering for this failure. A good approach that you can do is like list all your possible failures and all the possible attributes that can drive you to the failure. And then the way the code works, you'll be running regressions in all those possible trending attributes and calculating for each one your possible remaining useful life, and then switching, getting your worst case scenario, for example. So when you run this code, I mean, this code can be running R, for example. You can select your confidence level on the regression side. So you can use from 80% to 95. It all depends on how many data you have. But the confidence level, I mean, regarding the regression can go up to whatever level you want.
Yeah, a couple of questions. Can you take in, how easy would it be to take in the cost of operation of each booster each booster itself in the economic calculation?
Yeah.
You may have electric drives, you may have, et cetera, that each have a different.
Yeah. So actually we have been given two things, like latitude, longitude of each plant and each booster. And we have been given the gross profit margin of gross margin per MSFD on each plant. Okay, so we calculated. So they said the distance for each mile we are getting 2 cents. We are spending 2 cents for each mile. So it is very basic formula we made, because with the current constraint that the losing margin will be like, so the total cost will be current gross margin minus distance into 0.02 because that's 2 cents. So that's like profit margin we currently made, because now when we comes that portion of the booster go to plant A and portion of the booster go to plant B, then we have to make just one in calculation. We have to just add that percentage wise. Otherwise, there is nothing more to add in that one.
If we gave you a more sophisticated or a more accurate view of that cost rather than 2 cents a mile, it'd be relatively easy for you to plug in, and then you can drive the optimization off of that.
Yeah.
Second question is around have you thought about potential of doing an economic weighted health index? In other words, aggregating all these parameters and trends into a kind of a health index, but that could be economically or risk weighted to kind of give, again, prescriptive guidance on what to do and which one to go after.
Yeah. So actually, one more advantage of this booster efficiency we got. So there are 7-8 boosters. We have been in DJ Basin. There are 8 boosters. One booster is not running. So there are 7 boosters are sending to only 3 plants. So you can take out of 10 plants, 7 plants you can say running on very low, or you can make them shut down. So means it's saving percentage because the maximum profit you are getting by sending it to 3 plants. So with other 7 plants, the management can take decision based on whatever they want to do. Like they can put that in shutdown, but there's no loss they are getting. Like if you are running the plant empty, that is more loss than putting it in shutdown mode. That's what we think.
Any more questions from the panel? No. Thank you very much, gentlemen.
Yeah.
Great job.
Good job, guys.
Yeah, sure.